Okay, so thanks for sticking with me. We're to example 4, factoring polynomials in quadratic form. So factoring in quadratic form, we have factored polynomials that were x squared in quadratic form. So this is basically polynomials that have an even degree. X to the squared, x to the fourth, x to the sixth, x to the eighth. You kind of get the picture. So factoring these is the same. When you factor x squared, it pulls it apart into x and x. When you factor apart x to the fourth, it becomes x squared and x squared. X to the sixth, x to the third, x to the third. X to the eighth, x to the fourth, x to the fourth. Basically dividing the degree by 2. So in part A, we can do this the same way. Now this one's special because both terms are perfect squares. So this is a difference of perfect squares. So this is that pattern that we did a unit back. 16 as a perfect square, 4 and 4. X to the fourth is a perfect square, x squared, x squared. 81 is a perfect square, 9, 9. Now, with that, I think, for me, if you can figure that out, I am good to that point. Because we technically could break this one down, and I'll show it. But, I mean, I've already thrown a lot at you. I don't want to freak you out anymore. But this one is technically a difference of 2 perfect squares, which would turn it into 2x plus 3 and 2x minus 3. Because 4x squared as a perfect square. 9 is a perfect square. But again, if you can figure out the part where you make that connection, even is a quadratic form, we can factor it. For part B, before I do anything else, I can factor out a GCF, a common factor. I can factor out a 3, and I can factor out a p squared from each term. So this becomes p to the 6th plus 5p to the 3rd plus 6. So again, the highest degree inside of here is even, so it is in a quadratic form. So we can factor this in that same way. Numbers that add to be 5 multiply to be 6. Kind of had a brain fart there. Sorry, 3 and 2. So it's just the writing of it is a little bit different because p to the 6th split up, p to the 3rd plus 3, p to the 3rd plus 2. So it's really just how we pull apart that highest degree. Again, this is another one where it's going to be a little more rare than other types. Still showing you all the different types of ways you can factor. But again, factoring as a long-term skill, specifically, remember how to factor quadratics specifically and GCFs and things like that. The special cases become more and more rare unless you stick with math as a discipline, okay? So for what we're going to apply later on in this unit, the factor theorem is really going to be what I focus in on. So this has to do with synthetic division, which I think by now you guys probably have gotten pretty good at. So determining whether something is a factor, honestly, is just us doing our synthetic division. Seeing if this is a factor, let's do synthetic division with 2. And for this to be a factor, ask yourself the question, what does the remainder have to be? The remainder has to be 0. So, to do the synthetic division, drop down 1, this becomes 2, this becomes 4, 8, our remainder is 4. So, x minus 2 is not a factor. For it to be a factor, it would have to be a remainder of 0. So in this case, it is not a factor. Okay? It is not a factor. So it's kind of like us using substitution. If we substitute in and get out 0, it is a factor. So let's try it with this one. Substitute in -5. to test it out. So this progression goes 3, 15, -1, 0, and 25. The reason it is 0 there is because we skip a degree, okay, from x squared to the constant. So drop and multiply. -15, 0, 0, -1, 5, 5, -25, remainder of, ding, 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 0. So x plus 5 is a factor, okay? So you're looking for remainder of 0 for it to be a factor, because when we get crazy stuff like this that's not factorable in any other way, we've got to be able to factor it in more creative ways, I guess. So example 6, using this to factor. So first of all, showing that x plus 3 is a factor. Substitute in -3, and then go 1, 3, 0, -1, -3. So it's the fact that it says show that it is a factor, you know you did it wrong if you don't get a remainder of 0 in this specific example. So drop down the 1, -3, 0, 0, 0, 0 again, -1, +3, 0. So we did it right. We got a factor, or we got a remainder of 0. So to show this in factored form, x plus 3 is a factor, so I'm going to write it in parentheses, and then this result that we just got is a factor, so I'm going to write that in parentheses. So remember from before, this is x to the third minus no x squared term, no x term, but a constant term, okay? And for this, this is, I'm really sorry I did this to you. It's a difference of perfect cube, so it's that one I told you that isn't as common, which I'm going to try and use those less and less, because it's just trying to pick things that are going to be more useful to you guys later on, so I apologize for that one. But with this, it's remembering a is x, b is 1, so this is that one where we go x minus 1, a cubed plus ab, so x, 1x, plus b cubed, which is 1. So again, it's following that pattern from before. So I'm going to try and give you ones that are manageable, but again, this stuff, this is where the rubber hits the road in Algebra 2. This is where you really get down to the nitty-gritty of intense stuff that has a lot of information in a unit. So once we're back in person, I'm going to try and do a little bit more where I'm teaching you guys one-on-one, where I'm helping you a little bit more hands-on rather than hands-off, okay? I'm going to try and get a little more hands-on with stuff. We're still going to do lessons in a similar way. Not a lot has changed that way, but I'm still going to try and do more where I can target you guys and help you guys out more one-on-one. So you're probably ready to finish up the practice. The last couple questions on the paper and pencil practice, if you choose to do that, and then the checkpoint.